Hey everyone, good morning. Are you all there? If you can hear me, hey Haley. We're gonna start in 1 minute. I will be right back. Good morning. Yeah, I know online stuff is not ideal right now. It's not exactly what you signed up for. But you know, we're doing the best we can with what we have. So we'll see how it goes. We'll see how it goes. I'll be grading it this evening. Okay. Corey, I do like our name for him, or what did you say? Napoleon Bonaparte. I do need a jacket though. We need to get him a jacket, like a lab coat, and all that stuff. So, oh good. I'm glad, Carly. We need a jacket and a hat, like the 3-corner hat thing that they wore back in the day for whatever reason. Okay. Hey everyone. Good morning. What are we doing today? This is week 8. We are halfway through, so that's exciting. We are going to go over cranial nerves. We went over the basic parts of the brain last week. We went over dura mater, all the meninges and CSF and main brain regions. We're going to continue talking about brain regions as they apply to cranial nerves. A nerve, remember, the definition of nerve is something that extends out of the brain or spinal cord. It's peripheral nervous system. Nerve implies peripheral nervous system. Cranial nerve means it's hanging off of the brain. Cranial nerve means it's hanging off of the brain. Buy a Barbie doll with a scientist outfit? Find me one. Let me know. We can start a GoFundMe and buy all these outfits for them. In lab, you will form new groups. I will message your groups. So look up for a message later today. And you'll have to meet each other virtually. Again, I know this is rough being online when you didn't expect to be online, but I feel like one way we can make this easier on each other is if we work together. And if you have new contacts, if you have new people that you haven't been working with previously, now you have a bigger network of support. So we will form new groups. I will message you individually or as groups. Hopefully, Monday, Wednesday people, you've already turned in your lab checks, and Tuesday, Thursday, you'll be turning in by tomorrow. But turn in your lab check 8. Turn in your lab check 8 and activity 7. Let's write that down. Lab check 8 and activity 7 are due today. But in lab, we'll start the next lab check 9, and also the next activities, which I should pull up. Why have you logged me out? All right, while I'm figuring out my computer situation, let me know if you have any questions before we start. I will check the chat. Will we go over the quiz right now? No, we'll do that next time. I'll write that down for next time. You're asking me, Emilio? I'm okay. I'm hanging in there. It's hard waking up. I got to stay to a regular schedule. When will the quizzes be graded? Hopefully by this evening. I got a bit to do. All the answers were A. Is that intentional? I can't remember what the answers were, so. Do I plan on having the practical the same format as a quiz and it is timed? Yes, the practical will be, it's longer. I think it's 60 minutes, but 47 questions like always with 3 questions where we can't really interact with anything, but the best thing, or the closest thing I could get to interaction was having like a body and then labeling all the different muscles as A, B, C, or D, or E, or whatever. And then you have to choose the correct letter. So you're entering a letter for the activity part. But yes, same basic format. Any other questions before we get started? Ow. Damn it. Will this one have more histology than the last? This next practical. Man, I feel like I wrote this so long ago. What's on this practical? I mean, there's nervous tissue. So I think it's like about the same amount of histology. So you need to know your nervous tissues. Was it nervous tissues or muscle? It's all blending together for me. I got to check the topics, but it shouldn't. It's not going to be a lot. It's not going to be a lot. Oh, muscle? Yeah. So distinguishing like the different parts of a muscle fiber, what the striations, those A bands and I bands, what do you call it? Slow twitch versus fast twitch. So there's not a whole lot of histology, but and the connective tissue coverings. The connective tissue coverings will be good too. Did anyone take my advice to make cheat sheets while you do the quiz and upcoming practical? It'll be easier than flipping through all of your notes. You don't want to be spending time flipping through notes. If you just have it all on one sheet, then you know where to refer to everything. It'll be quicker. Okay, I'm going to get started. We'll find out, Haley. Let's get started. We're talking about cranial nerves. Cranial nerves, again, whenever we see the word nerve, nerve inherently means peripheral nervous system. A nerve is a collection of axons that extend out of the nervous system. A cranial nerve is a collection of axons that extend off of the brain. Where's my brain model? So when we look at the brain, look on the underside, that's where we can see all of our cranial nerves. We've gone over olfactory nerve, we've gone over the optic nerve, and we went over trigeminal. And there are a bunch more, or 12 total. So we'll go over all the nerves that are coming off of the brain, cranial nerves. Not only will we go over the nerves and what they do and their associated brain regions, but also what holes they go through. If they're coming out of the brain, that means they have to pass through the skull. And if they pass through the skull, that means there's a specific hole in the skull. Uh-oh, where's my pointy thing? There it is. So we'll also be looking at the base of the skull. We all know that this is foramen magnum. This is for the spinal cord. But then look at all these other holes. All those other holes are for cranial nerves. Well, not all of them, but many of these smaller holes are for nerves or blood vessels or both. So we'll be going over all of that. You've all been to the doctor, hopefully not recently, or without needing to for something serious, but you've all been to the doctor and they do something funny with you. They cover your eye and ask you to follow their finger, or they touch your face, or they ask you to shrug, they ask you to puff your cheeks out. They ask you to do some weird things as you, just to test things out. What are they doing? They're testing your nerves. Specifically, if it's around your face or your shoulders or your neck, all of these are tests for cranial nerves. So we're going to learn why do they make you puff your cheeks out? Which nerve would that relate to? Why do they gently touch your face? Which nerve would that relate to? Why do they make you shrug and resist? What nerve does that relate to? These are all tests to make sure that your nerves are functioning as normal. Whoops. Okay. So again, there are 12 cranial nerves. They come in pairs. So we've seen how like the olfactory nerve, there's one here, there's one here. So there's two, there are one on either side. They come in pairs, 12 pairs. They come out of this ventrolateral surface. This inferior aspect, that's the ventral ventral surface, ventral dorsal. So they're coming out of the ventral surface, and they're numbered 1 through 12. Hopefully you can brush up on your Roman numerals. We are going to be using Roman numerals for these cranial nerves. So an I for 1, XII for 12, 1 through 12, there are 12 cranial nerves that we'll go over. They mostly, for the most part, go in order. 1 is more rostral, 12 is more caudal. For the most part, there's a little bit of zigzagging. Like I mentioned, the brain is sitting in the skull. And so if these cranial nerves on the base of the brain are going out of the skull, that means we need holes in the skull. So what we're seeing here are the holes, the foramina. Remember, plural of foramen is foramina. And I've color-coded for you which foramina correspond with which nerve. So we've learned this already. The olfactory nerve, or I said this backwards, which nerve corresponds to which foramina? The olfactory nerve is going through the olfactory foramina found in the cribriform plate. What's another one that we've gone over? Actually, you know what? That's the only one that we've gone over. We're going to go over the other ones. Optic nerve goes through the optic canal, and the optic canal is found in the sphenoid. The ophthalmic nerve of the trigeminal nerve and the oculomotor nerve and the abducens nerve all go through the same hole. They all go through the superior orbital fissure. We'll go over all these things, but I just want to refer you to this for a quick guide to see which nerves correspond to which foramina. So we'll refer back to this. All right, first nerve. The olfactory nerve, cranial nerve number 1. Remember, it's just a Roman numeral I, cranial nerve 1. That's important for sensing smell. It's the only cranial nerve that's not attached to the brain stem. Every other single nerve is going to either midbrain, pons, or medulla, coming off of here. Olfactory nerve is the only one that's way in front. It's ending here at the olfactory bulb. You'll notice for every single one of these cranial nerves, I'll tell you where it starts and what hole it goes through and where it ends. So we're starting at the olfactory epithelium. Olfactory epithelium, here's your nose, here's your nostril, you breathe in. This is the olfactory epithelium. You've got nerve endings here. You've got dendrites here. These dendrites extend into the epithelium, and then the axon goes up to the olfactory bulb. Does anyone remember the shape? While I'm talking, I want you to guess. Does anyone remember the shape of these olfactory neurons, these sensory neurons? What is their shape? Your choices are pseudo-unipolar, bipolar, or multipolar. So the origin, again, is the olfactory epithelium. That's where you have your dendrites, your receptors, to sense smell. When you smell something, you're detecting chemicals. So anything in the air, anything that dissolves in the mucus of your olfactory epithelium. Corey, that's right, it's bipolar. What hole does it go through? We've seen this already. It goes through olfactory foramina of the ethmoid. Lots of tiny little holes. Lots of tiny little holes within the cribriform plate. So to look at this a bit more in detail, when we smell something, here's the path that it takes. We start here in the olfactory epithelium. That's where our dendrites are, where our receptors are. The neuron gets activated. It passes through the axon, which the collection of axons, that's what cranial nerve 1 is. A collection of axons, that's what a nerve is. A collection of axons in the peripheral nervous system. So here, this collection of axons, that is cranial nerve 1. Passes through the olfactory foramina, ends here at the olfactory bulb. So really, when we see the olfactory bulb, when we see this, really that's the end where the axon terminals are of that bipolar neuron. Another neuron then extends from the olfactory bulb through the olfactory tract. So here's a big difference. Nerve means collection of axons in the peripheral nervous system. Tract means collection of axons in the central nervous system. Here, we're officially part of the brain. So that's why these axons are part of the olfactory tract. These axons end in the olfactory cortex. Remember, the olfactory cortex is found in the insular cortex, that deeper region in the lateral sulcus. And then from the olfactory cortex, this is where we can process smell generally. So whenever something called the something cortex, it just means that's generally where that thing is processed. But it doesn't have to end there. We can send that information to think about what we're smelling. Like maybe we can try to identify what it is. Like I smell something and I identify that it's sweet. I'm like, okay, that's flowers or that's strawberries or something. So this is where we can send it to generally somewhere in the cortex. Don't worry about specifically where. It could be in tons of places. So we're just going to say generally somewhere in the cerebral cortex. Or sometimes we can send it to an area called the limbic system. The limbic system, we'll talk more about later in a minute, or talk in about a minute. But the limbic system is a collection of brain regions that are deeper in the brain. And they're generally important for things like emotions and memory. So when you smell something, sometimes you get that feeling like, oh, this reminds me of childhood, or oh, I'm disgusted, or oh, this feels great, just because of the smell. That's coming because we're transferring that smell information to the limbic system and we can process and associate things. Remember association fibers, where we send from one cortical region to another cortical region? This would be an association fiber. We're associating things. So not only can we identify what things are, but we can have feelings or memories about smells. Okay, what does limbic system mean? Once again, very broadly, it's important for emotion and memory. It's located just superior to the corpus callosum. There are three, I should actually say 4 main regions that are part of the limbic system. Remember, if you were checked the lab video the other day, here's our limbic system model. What this is representing, so like here's half of the brain, mid-sagittal cut, it's that, but obviously 3-dimensional. So this is representing the corpus callosum. All right, the first thing here is called the cingulate gyrus. The cingulate gyrus is found just outside of the corpus callosum. This is the cingulate gyrus. It's not a perfectly bordered area, but it's this area, the cingulate gyrus. Cingulate gyrus, very broadly, involved in emotion. I mentioned the other day that this area is affected, say, if you're addicted to something. It's important for a reward center, like feeling that feeling of reward. Just right above, superior to the corpus callosum. Cingulate gyrus. The hippocampus, this is Greek for seahorse. The hippocampus is this seahorse-shaped structure. Not this very thing at the end, this round thing at the end, just this thing here. So you can see the hippocampus from this view. I have another view for you. We can see it in a frontal cut of the brain, coronal frontal cut. So here's half of the brain. We cut the brain in half, and you can see this squiggly thing with gray matter. That's also hippocampus. We just took a slice of it at this part right here. The hippocampus, seahorse-shaped, involved in learning and memory. I mentioned movies like 50 First Dates or Memento. Those are movies where people had brain damage to the hippocampus. Like, that is a real condition where you can't form new memories. Yeah, seahorse-shaped. It's in the temporal lobe. Associated with the hippocampus, which I haven't included here quite yet, associated with the hippocampus are, you can see coming off of the hippocampus, hippocampus curling up, and then there's this tract here, the one that's arching up and around, and then terminating at that round thing here. This arch, this tract, it's a tract called the fornix. And Corey, yeah, dopamine is prominent within the cingulate gyrus. So the hippocampus connects to the fornix, which connects to the mammillary bodies. Hippocampus, fornix, following this curve that's going this way, and then ending here, this round thing, mammillary body. We can see this on the underside of the brain. The fornix is running along here, where this is this little arch. It's terminating at this round bulge that you can see on the underside of the brain, the ventral aspect. So these these two round bulges, those are the mammillary bodies. On our slide, hippocampus, fornix, mammillary body. Hippocampus, fornix, mammillary body. So all those are involved in learning and memory. Hippocampus, fornix, and mammillary body. That very round thing at the tip of the hippocampus is a separate brain structure. It's called the amygdala. The word amygdala means almond-shaped. So it's this round almond-shaped structure. What the amygdala is important for is for emotion and fear, specifically fear learning. So let's say you train someone or some animal that every time they hear a tone, they get hit or they get shocked. don't be mean and test with someone, but you know that it works. Yeah, let's say you pair a tone with a shock. You do that to a mouse. Every time you play, so you keep pairing the tone with a shock, keep pairing the tone with a shock. Then like 10 minutes later, you play the tone, but you don't shock them. They'll still flinch because they've learned that tone likely means shock. So they'll flinch and brace themselves for a shock. That's mediated by this brain region called the amygdala. It's important for fear learning. Any questions about the limbic system? Limbic system, set of brain regions, including the cingulate gyrus, hippocampus, and fornix and mammillary bodies, and amygdala. Okay. Oh, I want to show you one more thing. This will be important for our lab today. So take a quick look here. Okay, damn. Maybe you can see, remember olfactory nerve goes to olfactory bulb, from olfactory bulb, olfactory cortex to one of these other places. I want you all to learn this way to make a schematic of these pathways. How can we simply draw these pathways? Okay, let's say here's Corey and other people, you said that this first neuron in the olfactory, of the olfactory pathway is a bipolar neuron. To draw a bipolar neuron, dendrites, you draw as this open caret. And then draw the axon, or what's connecting to the cell body, extending in whatever direction. Cell body as a dot, as a filled in circle. Axon terminal. Draw an axon terminal as a filled in triangle. So dendrites as this open caret, cell body as a filled in circle, axon terminal as a closed triangle. So these dendrites here are in the olfactory epithelium. These dendrites are found in the olfactory epithelium and the cell body too. This axon, this is cranial nerve 1. That's the olfactory nerve, cranial nerve 1. What hole does it go through? It goes through the olfactory foramina of the ethmoid. How can we indicate that? I can draw a circle around this axon. I can just draw a circle like that, maybe not fill it in right where the line is. That I will signify as the olfactory foramina of the cribriform plate. Of the ethmoid. Yeah, we can get really detailed here. Okay, so what we've signified here, dendrite, cell body, axon terminal. It's in the olfactory epithelium and it's going through the ethmoid. Where does this terminate? Where is this axon terminal? Remember, it's in the olfactory bulb. So let's signify on our drawing of the olfactory bulb. Let's draw, we don't have to do that yet. Let's just draw another neuron. The next neuron, here's our first neuron. Our next neuron is going to receive input from that. This next neuron is in the brain. So the olfactory bulb is part of the brain central nervous system. The shape of central nervous system neurons is multipolar. To signify a multipolar neuron, remember we draw more dendrites, not just one set of dendrites like we did here for bipolar. For a multipolar neuron, 3 is plenty. 3 sets of dendrites just to show that there's a lot coming out of here. This axon terminal is communicating with these dendrites. Dendrites, cell body, axon. This is found this is the olfactory bulb. And this axon is forming that olfactory tract. This neuron terminates, we have an axon terminal in a region that we'll just draw out here. We'll call this the olfactory cortex. So this, our second neuron in this pathway terminates in the olfactory cortex. From the olfactory cortex, then we can do the same thing again. We got another neuron here that extends either to the cerebral cortex, or maybe it extends to the amygdala, or maybe it extends to the hippocampus. Could be branching to a bunch of different places, wherever it is we're going. So once again, I need you to get used to this type of drawing. Questions about this type of drawing, the schematic of how we can show neurons, shapes of neurons, where they're going, locations, how we signify foramina, stuff like that. I'm going to take a second to see if you have any questions. Questions? Questions? Can I get a confirmation that we're good? Cranial nerve 1. CNI is cranial nerve 1, olfactory nerve. Each foramen coincides with a specific nerve. Yes, each foramen coincides with either one nerve or multiple nerves, because some foramina are large enough that they can fit multiple nerves. Other questions? Just a reminder of what all these things mean. This thing means dendrites. This thing means cell body. This is the axon. Here's our axon terminal. And if we draw a circle like this, that means it's going through a hole. This represents a foramen. Cool? Okay. Cranial nerve 2. Cranial nerve 2 is for vision. It's your optic nerve. Optic nerve. So the origin of your cranial nerve 2 is the retina. The retina, we'll get into detail later, but the retina is referring to the very back of your eye. I don't have an eye readily available, but the very back surface of your eyeball, the very back surface of your eyeball is called the retina. That's where you find your photoreceptors, the receptors that detect light. The optic canal goes through a hole called, sorry, what did I say? The optic nerve goes through a hole called the optic canal. Where is my skull thing? All right, so here's your skull. Obviously the eyes go in here, but you see there's a lot of holes back here. Like there's this really long one. That's called the superior orbital fissure. It doesn't go through that. It actually goes through a smaller hole. Okay. See here? So it's not going through that fissure. It's going through a hole a little more medially. You can see it right there. Right here. See that? That's the optic canal. That's the optic canal. How do you find that? You can look at it from an anterior view in the orbit. From this basocranium view, superior view of basocranium. This is the sella turcica. So this is part of the sphenoid, the sella turcica. Look on either side of the sella turcica. So here's one hole. See it there? The other hole. The other hole is right here. Did I do the same hole? I can't even remember now. Anyways, that's the optic canal. The olfactory nerve, what you see cut off right here, cranial nerve 2, goes through the optic canal. Optic nerve through the optic canal. Where do these nerves go? They take a fun path. Some of these nerves cross over. Some of these nerves cross over. So what does that mean? If it's in your right field of view, so here's the right eye, because we're looking from an inferior aspect. If it's in your right field of view, that means it's either hitting this medial part of your right eye or this lateral part of your left eye. Right field of view, it's coming this way. Medial part of right eye, lateral part of left eye. It's coming from the right field of view. The way our brain processes things, in many cases, not all, but many cases, if it comes from the right, that means it's processed on the left. If it's coming from the right, so in the right eye, going to this medial part of the right eye, it will cross over to the left brain. But if it goes to the left eye, but it's in the right field of view, we can see that it stays on the same side. Does anyone remember the names for same side and opposite side processing? That's right, Saldi. Contralateral and ipsilateral. Contralateral means we're getting crossing over. The term for crossing over is called decussation. So we get decussation here at the optic chiasm. If it's in the right field of view, we'll cross over to the left. If it's in the left field of view, we'll cross over to the right. So there's some contralateral processing, but there's also some ipsilateral processing. So all that to say, we get some crossing over here at the optic chiasm. Chiasm is a crossing point. Chiasm means cross. We get some crossing over at the optic chiasm. Not everything, some of it, like half. We continue from the optic nerve, optic chiasm, then optic tract. Remember, nerve means peripheral, so technically this is peripheral nervous system. Once we get to the chiasm, we're officially in the central nervous system. Once we get to the optic chiasm, we're officially in the central nervous system, so now we call this a tract, optic tract. Was there another chiasm I've mentioned before? Not that I know of, just the optic chiasm. The optic tract continues to the thalamus. Specifically, within the thalamus, there's a nucleus. Remember, nucleus just means collection of cell bodies in the central nervous system. It's called the lateral geniculate nucleus. All right, why is it called the lateral geniculate nucleus? Lateral, because within the thalamus, it's lateral. The prefix, the root genu, means to bend, like at the knee. Like to genuflex means like to take a knee, like if you're in prayer, genuflex. So geniculate means it's this lateral bent-shaped nucleus. Lateral geniculate nucleus. It's found in the thalamus. So it's one neuron extending from, there is one neuron, there's other things more complicated that we'll get to later in the retina. One neuron extends from the retina, it's just one axon, it continues from the chiasm to the thalamus. So it's just one neuron from the eye to the thalamus. So it's a decent size. From there, we get another neuron from the thalamus that then extends to the visual cortex. The term for this axonal pathway from the thalamus to the visual cortex, those are called the optic radiations. So if I were to draw this out in our fun schematic, all right, so here's our eye. We'll get into this later, but I'm going to introduce it to you now. In the back of your eye, the first thing to detect light is called a photoreceptor. It's one word, photoreceptor. That photoreceptor then it's a special receptor cell. It's neuroepithelium. Remember neuroepithelium? It's really epithelium, but it's neuron-like. It detects stuff and then communicates with a neuron. This is neuroepithelium. Okay, so you have a photoreceptor that gets activated by the light. The photoreceptor then talks to another cell. It's called a bipolar cell because it's bipolar shaped. So here's our bipolar neuron, or bipolar cell. It's called a bipolar cell. So it's bipolar shaped and is called a bipolar cell. That bipolar cell then talks to another neuron. And this axon is really long. It extends out of the back of the eye. And this is what goes to the chiasm to the thalamus. This is called a ganglion cell. And this ganglion cell exits the eye, forming, this is the optic nerve. This is the optic nerve. This axon of the ganglion cell is the optic nerve, the collection of axons. It passes through that optic canal of the sphenoid, and it may or may not cross at the chiasm. So here's our optic chiasm. And then as it continues on, the axon is now called a tract, optic tract. It terminates in the thalamus, specifically the lateral geniculate nucleus. The lateral geniculate nucleus, LGN, of the thalamus. Then from there, we get another neuron. So here's another neuron. It's multipolar. And then this will extend to the visual cortex in the occipital lobe. And that's where we can process our vision. This branch is called optic radiations. Questions? Throw questions in the chat. Lateral geniculate nucleus. LGN is lateral geniculate nucleus. Okay. Cranial nerve number 3. We just went over Mackenzie, no, optic nerve does not go all the way to the visual cortex. I'll just show you again real quick. The optic nerve starts in the retina and ends at the chiasm. It is the same axon, though, that continues past the chiasm. This is the optic tract. And that one neuron ends in the thalamus. The next neuron that starts here in the thalamus, its axon, it's part of the optic radiations. So it's a different neuron, and it's no longer called the optic nerve. All right, cranial nerve number 3 is called the oculomotor nerve. The optic nerve was sensory. The olfactory nerve was sensory. Oculomotor, as the name implies, it is a motor nerve. So this isn't for sensing things, this is for controlling things. Sensing means bottom up. Controlling things means top down. Starts in the brain and then exits the brain to control something. In this case, we're controlling muscles of the eye. So the oculomotor nerve, where do we find it? Where's my brain? The oculomotor nerve, how well can you see this? It's not that big. See that one right here? I'm tapping it. You can see the 3. That's the oculomotor nerve. It's coming, this region, you can see it's above the pons. It's in the midbrain. So the oculomotor nerve exits from the midbrain. The midbrain is the origin. It's kind of near the superior colliculus. The hole that it goes through, is the superior orbital fissure. It's a really long, see how long this hole is? That's a superior orbital fissure. So a lot of things are going to fit through here because it's so big. Right here, this thing here, the superior orbital fissure. Where do its axons terminate? They terminate at several different muscles. Our eyes have 6 muscles to control their movement. Our eyes have 6 different muscles. You can see on this diagram up here, there's one for each side of the eye, and they're named after their location and the fact that they're straight muscles. These are skeletal muscles. We haven't gone over them, but here they are. There's the superior rectus, inferior rectus, lateral rectus, medial rectus. So if this is our eye, and here's the nasal bone, here's the lacrimal. Superior rectus, lateral rectus, medial rectus is hiding, inferior rectus is hiding under there. So there are 4 muscles that go on either side, but then there's 2 more muscles that attach kind of like at an angle. Like, can you see the right angle? There's one hiding that's going from down to the side, it's swooping off. And then the other one here, this isn't connected the best, give me a second. The other one here, you can see it's tendon. This tendon attaches, and then the muscle is off to the side. But this, it's supposed to connect. This is the tendon of another muscle. Those 2 muscles are known as oblique muscles, superior oblique and inferior oblique. It's so you can roll your eye. Okay, so in short, wasn't very short. In short, there are 6 muscles that control movement of your eye. The oculomotor nerve controls 4 of those. You should know which 4. The oculomotor nerve controls the superior rectus, so you can roll your eye up. Inferior rectus, so you can roll your eye down. Medial rectus, so you can look towards your nose. Inferior oblique. Inferior oblique is starts medial and then attaches off to the side. So when you pull it, you can look like up and to the right. It rolls up to the right. That's inferior, or is it inferior oblique? It's those four muscles for eye movement that the oculomotor nerve controls. There's another muscle that isn't about eye movement, but more about eyelid movements. So lateral rectus and superior oblique are going to be different nerves. They're going to be controlled by different nerves. So here's our eyelid. The word for eyelid is palpebrae. The word for eyelid is palpebrae. Palpebrae, or that's plural, palpebrae. So to lift up your eyelid, when we move our eyes, or our eyelids, it's really the top one that's going up and down. So the muscle for moving your eyelid, that's called the levator palpebrae superioris. It opens the upper eyelid. Levator palpebrae superioris. So the oculomotor nerve controls that too. On our diagram here, here's our eyelid, here's the muscle. You can see the nerve, here it is, oculomotor nerve branches to it. So it controls your eyelid. Oculomotor nerve controls something called ciliary muscles. You know how you can all see my pupils? My pupils constrict, pupils dilate, constrict, dilate. There's a muscle that's controlling that, mediated by a nerve. The muscle is the ciliary muscle. I'm sorry, no, gosh, I messed it up already. It's not the ciliary muscle. I'm pointing out the sphincter pupillae. The sphincter pupillae muscle, that's what's controlling your eye opening, your pupil getting bigger and smaller. So pupil constriction for the black hole of your eye to get smaller, that's controlled by the sphincter pupillae muscle. That's mediated by the oculomotor nerve. So I'll say that again. Oculomotor nerve controls your pupillary reflex. When you shine light on your eye, get different amounts of light, your pupil can get bigger, it can get smaller with more light. It's controlled by the sphincter pupillae muscle, which is controlled by the oculomotor nerve. Ciliary muscles, let's see if I can do this. Like when you hold something in front of your face and you focus on it, so I can focus on this thing, but I can also focus in the distance. I don't know if you can see my eyes changing at all, but my focus is changing. I'm focusing in the distance right now, not focusing on the thing in front of me. To do that of course requires muscles because you're changing something. What are you changing? Inside of your eye, you have a lens, and you can change the shape of that lens. The term for changing the shape of your lens, that's called accommodation. And the muscles that are inside of your eye that change the shape of your lens, those are called ciliary muscles. They look hair-like. Here, I can show you. All right. Yeah. So I took out the eyeball. And then if you cut the eye open, so make a frontal cut and look inside. These muscles here, these hair-like muscles on the inside, they're attached to the lens. They're attached to the lens. So when these muscles contract, you're changing the shape of the lens. When you change the shape of your lens, so in other words, when you focus on different things, that's what accommodation is. And these ciliary muscles, which you can see this is the anterior view of the eye. I've cut the eye in half, and now we're looking on the inside. These hair-like things, it looks like the underside of a mushroom. These are the ciliary muscles. They attach to the lens. They attach to the lens and control shape. So there's a lot there. The oculomotor nerve is important for a lot of different things. Moving our eye in 4 of 6 ways. Opening our eyelids, accommodation, which means focusing on things, and pupil constriction, the sphincter pupillae. Controls all those things, but all relating to the eye. Questions? Let me know. So I said that the oculomotor nerve comes out of the midbrain. I haven't talked a whole lot about the midbrain, so let's talk a little bit more. The midbrain, very generally, because it's part of the brainstem, it's very vital. It's important for maintaining consciousness and alertness. So it helps keep us awake and alert. Here is a posterior view of, where's my brain? Here's a posterior view of the brain. So dorsal posterior view. So if we're looking on the back side of the brain, if I remove the cerebellum, we're looking at this surface. Remember these two bumps? These two bumps, those are the corpora quadrigemina. This region is the midbrain. We're looking on the back side of it. So here's our corpora quadrigemina. Specifically, the superior colliculi, here you can see the nerve coming out. The superior colliculi, that brain region of the midbrain, that's important for the visual startle reflex. Like if you see a flash of lightning and you flinch, or someone flashes you in the eyes or the camera and you flinch, that flinching response is controlled by the superior colliculi. Those two bumps of the midbrain. Okay. Fourth nerve. We're on to 4. Remember, 4 in Roman numerals is IV. So 3 was just 3 eyes. 4 is IV. It's 1 before 5. The trochlear nerve controls the superior oblique muscle. It only controls one eye muscle. Because it only controls one, it is the smallest cranial nerve. It has the fewest axons. Trochlear nerve. We've heard this word trochlea before. Can anyone remember where I've mentioned this word trochlea and what it means? Anyone? Humerus, yeah. Remember the humerus? There's that rounded protrusion at the distal end. It acted like a pulley. The word trochlea means pulley. Yeah, the word trochlea means pulley. So where do we have a pulley? In our eyes or outside of our eyes? Give me a second. Oh, no wonder it's broken. Exciting. Okay. So here's our eyeball. See the tendon? This tendon loops through a little like thing. It loops through something. The tendon goes through something and then follows along the side, the medial side of the skull here. This is one muscle and its tendon loops and hooks back. So it's acting, this little hook is a pulley. That little hook is called a trochlea. On our diagram here, here's the muscle. The tendon goes through this bony hook called the trochlea and then attaches to the eye. So that means if, let's say I'm the eyeball, there's a muscle that it goes this way, but then it attaches right here. So when it pulls, it's gonna make my head roll. It's gonna make the eye roll. The superior oblique is to help you roll your eye down and in, medially and down, rolling your eye, just in that one direction. The origin is near the inferior colliculus in the midbrain. The foramen is also through the superior orbital fissure, that same large hole, superior orbital fissure. The destination is the superior oblique. Destination superior oblique. So following on here, here's the nerve, ends at the superior oblique. Here's a muscle, goes to the trochlea, attaches to the eye, off to the side. Take a moment. Gone through 4 nerves now. Take a moment. Okay, which nerve would cause the eye to drift up and in? Like you're looking at the spot between your eyebrows. If your eye is drifting up and in, that means normally you'd want to turn your eye down and in. Oh, we lost sound.